Hello guys, in this video we will learn how actually gradient descent works on neural network with the help of backpropagation. Okay, so this is going to be a detailed video. Please listen to it carefully so that you will have no doubts how we calculate the gradients. Okay, so let's get started. So let me just quickly recap how gradient descent looks like in case of machine learning. So in case of linear regression, we have our hypothesis theta transpose x, right? And our cost function is this j of theta equal to 1 by 2m summation over I equal to 1 to m. We take the square difference between the actual and predicted value for all the training examples and we take the average. So this is our cost function. This is also called as mean squared error. And our aim is to reduce this cost as much as possible, right? We have to arrive at this particular point which is called as global minimum. In order to do this, in order to reduce the cost, we have something called as gradient descent algorithm, which will update these thetas. These are the parameters in case of linear regression or logistic regression, and this will update thetas by following this particular set of rules, right? So this is how we did gradient descent with respect to machine learning on linear regression. So it states theta 1 is equal to theta 1 minus alpha into how loss changes with respect to change in theta 1. So that's what d by d theta 1 of j theta means. Similarly, theta 2 is equal to theta 2 minus alpha into how loss changes with respect to change in theta 2. Theta n is equal to theta n minus alpha into how loss changes with respect to theta n. So this is what gradient descent does in machine learning linear regression or logistic regression. Now coming to this particular neural network where we have three layers, two hidden layers, one output layer, one input layer, right? So we have our activations associated with layer 1 as A1, with layer 2 as A2, with layer 3 as A3. Okay. Now we have, instead of thetas, we have weights and biases associated with each of these layers, right? So we know that we call this as W1, we call this as W2, we call this as W3. Similarly, we will have biases B1, B2 and B3, right? And whatever output we get, that is A3, these are also called as our predictions. We will plug this as input to our loss functions, and our loss functions would be calculating the how close the predictions are with the actual values and then coming to some value that we call it as loss. And these loss are influenced by weights and biases. Why? Because our predictions are influenced by weights and biases. Okay, hope you guys are clear on this part. Now coming to gradient descent application on neural networks. How do we do that? The formula remains same, guys. So we repeat some steps until convergence. Convergence of what? Instead of j theta, we say jw comma b. This is our cost function in case of neural network. So we need to arrive at global minimum for this particular cost function. This is jw comma b. So in order to achieve that, we will have some set of rules, and these are the rules. What? Weight at layer 1, weight matrix at layer 1 is equal to weight matrix at layer 1 minus alpha into how this cost is affected by changing weights at layer 1. Okay. Similarly, weights at layer 2 will be updated as weights at layer 2 minus alpha into how this cost is affected by changing the weights at layer 2. Similarly, we go till the last layer and then update our weights following this particular rule. Similarly, we do the same steps for our biases as well. So for this video, I am not talking much about biases. We will just see how we will update the weights and what are these derivatives. So when I say what is the effect of change in W on this cost, this is called as derivative of cost with respect to weights, right? Then we will have multiple layers on the weights. So we will calculate the derivative of loss with respect to weights on each layer. So instead of calling them as derivative of loss with respect to weights every time, I just call it as what is the effect of change in weights at layer 1 with respect to cost. So this will make things much simpler in order to understand. Okay. So now let's see how to calculate these derivatives. These derivatives are nothing but our gradients. So we have to compute these gradients now. So in order to understand and derive these gradients, let us go back here, right? I have drawn the same neural network architecture as we have seen below, and I have written some formulas here. Okay, so you see this particular loss or cost. So let me clear the difference between loss and cost. Loss is associated with only one training example. Cost is the average of loss over all the training examples. Okay. Now, in order to explain back propagation and how to update the weights, I am considering only one training example. So I am calling it as a loss in my further explanation. Please don't get confused. Okay. Now what we have to do in order to apply gradient descent, we have to back propagate in a way that we have to calculate the effect of change in weight 3 on loss. We have to calculate the effect of changes in weight 2 on this loss. Similarly, we have to calculate the effect of change of these weights on this particular loss. Right? In order to do this, I have taken out this particular section here, what I have highlighted here, right? And converted this into a computation graph. This we call it as computation graph. Okay. So I have written one feature x1. We feed that as an input in order to calculate our activations at layer 1. So f is some activation function. We do not know what that activation function is, but this is to introduce some non-linearity in the network. So I'll talk more on that in my other videos, right? So we have input x1, multiplied that with the weights associated with that particular layer w1, and we will add the bias term with that particular layer b1, and this together we call it as z1, and we apply some activation function on top of this, and we finally call this as a1. Now that we have calculated the activation function at layer 1, we will pass on that activation as input in order to calculate the activation at layer 2. So what we do, we take the output from the previous layer, that is A1, multiply that with the weights on that particular layer W2, plus we will add the bias B2, right? We call this particular thing as Z2, and we apply some activation function F, we call it as A2. So this is our A2. So finally, since we have 3 layers, this will be our last step in forward propagation. What we do, we pass A2 as input to our calculation for calculating our A3. So what we do, we multiply A2 with the weights associated with layer 3, W3, we add the bias B3. We call this as Z3, and we apply some function, activation function, and call the resulting output as activation at layer 3. And we make use of this activation at the final layer as our predicted values and supply it as input to our loss function and compute the loss. Okay. Now in order to minimize the loss, we know that we have to update these weights. How do we know? Because we are applying gradient descent and we have seen this in our below algorithm. We have to update the weights in order to reduce the loss, right? So in order to update this, we will follow certain rules as I told you, right? So what are those rules? Weight 1 is equal to weight 1 minus alpha into how the loss is affected by changing the values of weight 1. Similarly, weight 2 will be weight 2 minus alpha into how the loss is affected by changing the values at layer 2. Similarly, how the loss is getting affected by changing the values at layer 3. So this is what we have to compute now. So in order to do these computations, I have written some table here which is simple. So first column is functions. So loss is a function, one kind of function for us, right? So I have written that down. A3 is an activation function at layer 3, A2 is an activation function at layer 2, A1 is an activation function at layer 1. So that I have written is the first column. And subsequently I have written what are the inputs to those functions, right? For loss, input will be A3, right? And of course we will supply our two actual values. I will keep that aside because we are not concerned with the actual values right now in order to calculate the gradients, right? For A3, the inputs are A2, W3 weights and B3 bias. Similarly for A2, inputs are A1, W2 weights, B2 bias. And for A1 input is X, W1 is weights associated with the layer 1 and B1 will be the bias associated with layer 1. So these are the inputs for our functions which I have listed here in the first column. Now this X, this is not a variable, this is a constant, right? So we have our input data fixed, we will not intend to change that, we will not intend to modify those values in any way, right? Apart from this, everything here is a variable. Why I am calling it as variable? Because we can update weights, we can update biases, which will have the repercussions on how we compute A2, A1 and A3. Okay, so that's why except X1, everything is called as variable. Okay, now in the back propagation, I am talking about first step, how this loss is affected by change in the value A3. How do we write that in terms of mathematics? We write it as dl by dA3. How the loss is affected by changing the values of A3. So this is simple, y minus A3. Y is our actual value. Okay. So this is how we calculate how the loss is affected by changing values at A3. So this is done. The first calculation is done. Now we have to calculate how this loss is affected by change in the values of W3. So in order to do that, what we will do, we will come to this particular table. Okay. So what we have to calculate, let me just rub this, I'll write it again in a neat way. So we have to calculate how the loss is affected by changing values at layer 3 weights. Okay. So this can be given as how the loss is affected by change in values of A3 into how the A3 values are affected by changing the values of W3. So this is what we have to do in order to calculate the gradients at layer 3. So this dl by dw3 is called as gradient at layer 3. Okay. So that we have computed right now. In the same thing I have written here. dl by dw3 equal to dl by da3 into da3 by dw3. Okay. And this dA3 by dW3 can be expanded further because A is obtained by applying activation function on Z3, right? So that's what I have written here. So if you want, you can refer this. I'll just tell it to you guys for the sake of explanation. So how to calculate this, okay? So we have A3 is equal to W3 into A2 plus B3. We call this as Z3 and we apply some function and then call it as A3. Now in order to calculate the effect of weight change on A3, we need to calculate the effect of change on A3 when Z3 changes, multiply that with the effect of weights on Z3, then we will get effect of weights on A3. So that's what I have written here in the end, right? So this is how we calculate the gradients at layer 3. So this is simple. It's not complex and it's very easy to understand also. Now comes the part where things get bit complex when we have to calculate the gradients at this particular layer, that is dl by dw2. Okay. So in order to calculate this table will help us greatly. So that's why I have written this table. So we have to calculate the effect of change of W2 on loss. That's what the gradient at layer 2 indicates. So in order to do that, we have to consider everything that comes till this particular weight 2, right? So let me just write that down here. So the effect of change of weights at layer 2 on loss is given as effect of change of A3 on loss, okay, multiplied by effect of change of weight 3 on A3, okay, then effect of change of weights 2 on A2. So that's what I have written here. So as we calculated effect of change of W3 on A3, Similar way, we can calculate the effect of change of W2 on A2. So that's what I have written here. So effect of change of weights 2 on A2 is given by, it's a multiplication of effect of change of Z2 on A2 multiplied by effect of change of weight 2 on Z2. Okay. Then we will plug in these values for computing our dl by dw2. So this is our final equation. So what it is? So if you write it everything in an expanded way, it is rate of change of loss with respect to rate of change of A3, rate of change of A3 with respect to rate of change of weight 3, rate of change of A2 with respect to rate of change of W2. We multiply all these things in order to compute our rate of change of loss with respect to rate of change of weight 2. So this is called as gradient at layer 2. Layer 2. Okay. Now we have computed gradients at layer 2. Similar way, by following the chain rule, we can compute the gradients at layer 1. Remember, this x1 should not be considered as variable. So we will not consider this particular x1 in our calculation to calculate the gradients associated with layer 1. So see how we are propagating back from layer 3 to layer 2, layer 2 to layer 1. That's why we call it as back propagation. Okay. We are going back in time somehow, right? So that's a fancy term. So we call it as back propagation. So in order to calculate the rate of change of effect of rate of change of W2 on loss, W1 on loss, what we have to do? We have to multiply the effect of rate of change of A2 on loss, effect of change of weight 3 on A3, multiply the effect of change of weight 2 on A2, finally multiply the effect of change of W1 on A1, right? So that's what we have to do. In the end, we will simply call it as the gradients at layer 1. Gradients at layer 1 is computed as effect of change in weight 2 on loss multiplied by effect of change of weight 1 on activation function A1. So this is what I have written here in an expanded way. So this is what our gradients or derivatives are with respect to weights and J or L, you can call it as. Now I have explained it to you guys by taking just one single example and one neuron. We will repeat this for entire neural network architecture by considering all training examples M, right? So the same logic applies for all the weights and the biases associated with each layer. Okay. So guys, hope this is clear. And how we arrived at this? We arrived at this with the help of something called as chain rule. Okay. So if you guys have not watched my previous video where I have explained computation graph and chain rule, please go back and refer that. Then this video will make more sense. Okay. So now we have the values for this gradients. We will plug in this rules and we multiply this with alpha. Alpha here, as you know, in machine learning, it stands for learning rate. Here also it stands for learning rate. So we multiply that with our gradients, computed gradients, and then subtract that with our existing values at that particular layer. And then we will get our new value for the weights. Using those values, we will again do a forward pass, right? Do the forward pass, compute A1, A2, A3 loss. Again do the backward pass, update the weights. Do the forward pass, compute the cost. If it's not minimum, again do the back propagation. Repeat this process. So we have to repeat this process until we arrive at a global minimum. Okay. So hope this is clear, guys. I have taken some effort to explain this, to explain it in a simple way, as simple as possible. If you guys have any questions, please reach out to me in comment section. I'll try to explain it in a more easy way for you guys. Okay. So if you guys are not subscribed to my channel, please do subscribe. And if you like the content, please share it with your peers so that they will also be profitable with this. Okay. So they will also gain some knowledge. So thanks guys. Till we see in the next video. Happy learning. Bye bye.